Hi, I'm Zach, and I'm the CTO of the Aztec Protocol. We are a privacy provider for Ethereum. And what we do is we enable private smart contracts and private digital assets on the Ethereum mainnet through the use of zero-knowledge cryptography. And I'm here to talk about what? I'm apparently nothing. Hang on. Oh, I went the wrong way. There we go. Okay. Yeah, I'm here to talk about Plonk, a new snark construction that we've developed in collaboration with Protocol Labs and Ariel Gabazon, who's right there. Yeah, so this is a new snark construction that removes a lot of the difficulties and problems that we're having deploying snarks to into production today. Specifically, just to recap about snarks, snarks enable verifiable private computation. So they're useful for privacy, for obscuring, for having smart contracts with private inputs. They're useful for scaling if you want a transaction to actually represent tens of thousands of transactions, and you want to very efficiently verify that these transactions have been performed correctly. However, existing state-of-the-art snarks typically require this trusted setup process. This is a procedure where you need to generate a reference string with some secrets called toxic waste, and if those secrets leak, then your cryptography is insecure. And in the context of blockchains, that typically means people can steal money from your system, which is pretty bad. There's been a rise recently in the concept of universal snarks. These are snarks where you don't need one trusted setup per snark program, but you need one per just for the entire crypto system, and then you can create arbitrary programs that you can compile down into snarks without having to run additional trusted setups, which massively reduces the risk and difficulty of deploying these crypto systems. This was the first universal snark construction was a couple of years ago. It came up then. Sonic, if you've heard of it, came on its tails. But these have all suffered from being impractical to deploy because the proof construction times and the proof verification times are just too high for mainstream use. Plonk, however, is a little bit of a different kettle of fish. And what I want to go over is a little bit about the technical nitty-gritty of actually what is a Plonk snark? How do you make snarks? What does it do? Why does it do what it does? And so at its core, when looking at the building blocks, what do we need from a snark? We need a way of representing some kind of program that we want to verify we've computed correctly. We want to represent it via some kind of arithmetic gate, some fundamental operation like a logic gate, but one that's more amenable to kind of elliptic curve-based crypto systems. We want to then commit to this. So basically, no matter how complicated our program, we want to be able to compress down this proof of computation into something that's constant size, so a kilobyte or less. And then we want to be able to efficiently evaluate whether a certain computation has been correctly performed, whether the arithmetic, the arithmetic equations for each gate hold. And we want to do that in parallel for millions of gates with a single equation that can be efficiently and easily tested for. So, easy stuff, right? How do we actually do this then? So, the fundamental technique that Plonk uses is we take the variables that are going into these arithmetic gates that define your program, and we represent them as vectors. And then we encode these vectors as polynomials, because polynomials are a very natural way of representing information in modern crypto systems, because we have ways of being able to represent a polynomial with arbitrarily high degrees with a single elliptic curve point. And we can very efficiently evaluate these polynomials. So you can prove that a polynomial evaluated at a random point is equal to some large number. And this enables us to convert vector arithmetic into polynomial arithmetic because of a rather useful property of polynomials, which is that if you have some kind of relationship between polynomials, if you evaluate these polynomials at a randomly chosen point and check the relationship with the evaluation, so just large numbers, if that evaluation holds, then with overwhelming probability, the arithmetic relationship you're checking for will hold across all evaluations of that polynomial. Obviously, terms and conditions apply, so many terms and conditions, but that's the general gist of it. So, okay, how do you take a vector? How do you encode it as a weird polynomial? Well, we use something called Lagrange basis and Lagrange interpolation. Specifically, if you have some vector with n elements, then you just take some x coordinate, like some predefined x coordinates. So here I've done from 0 to 9, and you create an interpolating polynomial, basically a line which will cut through at each x-axis, x-coordinate value, the y-coordinate will be equal to one of your vector elements. That'll give you 10 points on a line. You draw an interpolating polynomial between them, and that's your Lagrange-based polynomial. So you can then take a linear sum of these polynomials to represent your entire vector. The reason why this is useful is because it allows you to very efficiently test for arithmetic relationships. So this is a bit of a lot's going on in this slide, but hopefully I can try and disambiguate some of it. Specifically, what we have here are, I've taken some polynomials that represent vectors a, b, and c, and I want to test that a times b plus c equals 0, that's a multiplication gate, for every element of each vector. So the red polynomial is a, the blue polynomial is b, the orange polynomial is c. And it's a little bit difficult to see, the unifying factor between all of them is that the elements of each vector are encoded as y values that these polynomials resolve to at like the x values from 0 to 9. And here's the thing, if the arithmetic relationship holds, if that thing is 0, then it means that if you perform that arithmetic over polynomials, then the resulting polynomial you get will be, look a little weird, but the unifying thing about it will be that it will cut through the y-axis at all of those x values, because if you consider like the point evaluations you're doing, they all resolve to 0. Why is this useful? This is useful because it means that you can perform an arithmetic test over millions of vector elements simultaneously by checking one polynomial relationship, because you just check that the resulting polynomial arithmetic is equal to 0 modulo this thing called the vanishing polynomial. A vanishing polynomial is just the lowest degree polynomial you can find that will cut through the y-axis at all of the x-coordinate x points that you've considered to be important. And this is the way we kind of compress enormous amounts of information into a very simple arithmetic relationship. So if we can encode vectors as polynomials and we can perform vector arithmetic with create a proxy for vector arithmetic with polynomial arithmetic, the next question is, how do you actually make a circuit out of this? What is addition gates, multiplication gates? What is this? What do they mean in a vector world? So it's relatively straightforward now because we can just talk about vectors instead of those weird polynomials. Effectively, what you do is you just define gate constants for each gate. So M stands for multiplication, O stands for output, C stands for constant. The idea is you can scale the wire values going into and out of these gates by constant values, and then check the whole result resolves to 0. And you can do the same for multiplication gates and addition gates, and just the arithmetic just becomes slightly different, but it's relatively straightforward. The problem is, though, we don't really want two equations that we test for. We want one, because if you have two relationships you're testing for, then you have twice the amount of data that you're having to send to a verifier. It means probably roughly twice the amount of work, computation that a proof constructor has to do. So we'd rather get rid of that. So what we do instead is we create a single arithmetic gate that represents both addition and multiplication. The idea is basically you can just send various values of these gate constants to 0 to either turn on or off the addition terms or the multiplication terms. So where does this get you? Well, it gets you to what we have on the right-hand side, where you can take this this arithmetic relationship over these vectors that just has additions and dot products, and you can map it into a polynomial world, where the same arithmetic relationship is now equal to 0 modulo this vanishing polynomial. And then you can evaluate these polynomials at a random point, then test this one equation just once, and test it holds. And by doing so, you've actually validated that the vector equation on the left-hand side is valid. And those vectors can contain millions or tens of millions of elements, and you've compressed it down into a single, succinct check. And here, for anyone who's interested, Li just stands for Lagrange interpolating polynomial. So it'll be equal to 1 at one particular x value. Right. So we're halfway through. Sorry. For the high pace, feel free to heckle and ask questions if there are things you don't understand. What is missing from this now? We can take a step back and think, what have we done? Well, we can now efficiently evaluate the arithmetic relationships for addition and multiplication gates, and we can validate large numbers of them at once. However, that really just gets you to the bottom situation where you basically have all of these gates with little wires sticking out of them, and you can check that each gate related, like the Y values for each gate, satisfy that arithmetic check we had. But that doesn't describe anything useful, because an actual program, a circuit, well, the wires are going to be connected to one another, and they're going to be connected in higgledy-piggledy, random, non-linear, confusing ways, because probably the thing doing making those connections will be a compiler, not a human. So how do we get to this world? How do we define relationships between these wires that don't neatly fit into these kind of arithmetic gates? And the trick is to use copy relationships. So to kind of elucidate what I mean, if we consider this toy example on the left where you have two gates, it looks like there's one wire connecting the outputs of the first gate into the left wire of the second gate. But that's, for the purposes we're about to describe, that's actually two wires. There is the bottom gate has an output wire, the top gate has a left wire, they just happen to be the same. And we need a way of testing this. And so for a given, so we can kind of try and sort of represent this by looking at considering the vector of all the wire values in a circuit. And considering for a given program, for a given circuit, there's some of those wire values are going to need to be equal to one another because that represents a connection between the wires. And we need a way of testing that. And the way that we came up with Plonk was a similar argument method that previous SNARK constructions like Sonic have used, which is it's called a permutation. Effectively, we want to create two polynomials where the roots of these polynomials are identical to one another if and only if these copy relationships are satisfied. We want to do this because that's something we can efficiently test for and check for, and we can do it without doing any like crazy shenanigans that require program-specific like trusted setup processes like other SNARKs, which that's how they kind of handle this problem. But we want this to be universal, so we can't. So we map the wire copies to we define copy relationships with permutations, because if you consider a vector of wire values, you can consider each wire to be mapped to a unique index. So just W1 will map to 1, etc. We can then define this kind of a permutation function. The idea of this is what the permutation function will do is when you feed it in a wire index, it'll spit out the index of another wire in that circuit that is a copy of the input wire. And so to give a toy example here, if you have a circuit where the first, the third, and the fifth wires are equal to one another, then the permutation function will map 1 to index 1 to index 3, it'll map index 3 to index 5, and it'll map index 5 to index 1. So that cycle is closed, and the only way that mapping holds is if the wire values are the same. We can then create a kind of a counterpart to that vector of wire indices, which is just a vector of all the indices after they've had the permutation function applied to them. The idea here is what we want to do is we want to then kind of put this all in a blender. We want to mix up the wire values, combine the wire values with their kind of index values, and also combine the wire values with their kind of their copy counterpart values. And if we do this correctly, then the resulting kind of scrambled mess will be only will only be equal to one another if and only if the copy relationships are satisfied. To try and to articulate this a little bit, what we're really doing is computing these product terms, where we're taking the y values. Does this thing have a pointer? Yeah, no, never mind. Taking the y values, combining them with an element of the permutation vector, or call this the identity vector. And then we're just multiplying them all together and adding a bunch of randomness to make sure that you get these very random linear combinations of both wire values and vector indices that will only be equal to one another if the wire values obey the copy relationship. To try and elucidate why this actually is the case, again, we can rely on what I talked about earlier when it comes to polynomial testing. If some polynomial relationship holds at a random point, it holds at every point. So we've added random terms into these product terms at the top, beta and gamma random variables that are generated effectively by the verification algorithm. And you can consider beta and gamma to represent, well, to start with, let's take gamma. That random number can be mapped to some kind of polynomial, indeterminate variable in a polynomial. And so we have two polynomials here that if these product terms are equal to one another, then it means that these polynomials share common roots. Which means that we can then take one of the roots in the first polynomial and look at its matching counterpart in the second polynomial and consider what that means. Well, now we have two terms in like y values and y of indices and these beta values. Again, beta is random, so you can consider these as 2-degree 1 polynomials that happen to be equal to one another. Therefore, the coefficients are equal to one another, which means that the takeaway from this is if all of this mess holds, the y value wi will be equal to the y value wj when the permutation function maps index j to I. So what this is basically saying, if y is 1 and 3 is supposed to be equal to one another, then you can't create these product terms that match unless you've correctly followed that instruction. That's all a little bit. The permutation argument is quite unintuitive. I must admit, and it's something that I do have difficulty explaining. But it is kind of critical to why we can create efficient snarks without having all these repeated trusted setups, because it allows you to describe relationships between all of these y values, which typically has been the stumbling block. Of course, I've been talking about vectors and permutation vectors and products of vector coefficients, vector elements, but we actually have polynomials, which is a bit of a problem because we can quite efficiently take those permutation vectors and turn them into polynomial counterparts, and then we can kind of emulate that product term I had from the previous slide, where because we wanted to consider all y's in the circuit, and we actually have polynomials that represent left, right, and output y's, we can just take their products, and these resulting polynomials, let's call them z1 and z2, their coefficients, like the Lagrange coefficients, the y values on a graph when the x values are equal to the special interpolation points, they will be equal to each of the terms in our grand product argument. They will be equal to each of the terms in that product up there. But the problem is we want to compute the product of all of the coefficients. We don't just want to represent these coefficients as polynomials. We want an actual scalar value. How on earth do you do that? The grand product argument for this permutation check is itself a form of a snark circuit, where effectively what we're doing is we just have a chain of multiplication gates, and we're just feeding in each grand product, like each permutation product term on the right wires, and concatenating them all together into some product. But this is a bit paradoxical because now we need a permutation argument to validate a snark circuit, but the permutation argument itself is a snark circuit. But because it's very simple, we can kind of get away with a shortcut, which is in every single gate in this circuit, the left wire of the current gate is equal to the output wire of the previous gate. So if you represent all of the left wire values as a vector, then all the output wire values will be the same vector, but just shifted one to the right or to the left. It's to the left. But how do we perform this shift on a vector? Because we don't have vectors, we have polynomials, right? We've constructed these weird Lagrange interpolated polynomials, and now we want to kind of, using the same polynomial, we then want to kind of represent that vector, but where all the coordinates are shifted, which is a little bit tricky. It's one of the this was something that came to Ariel when we were chatting in a conference in London, and this is really the kind of the inciting incident for Plonk, which was if you have consider the nth roots of unity, because bit complicated, but when I talk about Lagrange interpolation, I talked about picking special coordinates on the x-axis that are going to represent elements of our vector. And those special coordinates are the roots of unity, because we're working in large prime fields, finite fields, in order for this to be secure, where basically you just have a number line which wraps around on itself at a large prime number. And in that kind of world, you can find very high degree roots of unity, because you just find some number where when you multiply it by itself n times, it just wraps around the number line until it ends up on 1. And so to kind of give an articulation about how we can perform shifts of vectors even though they're represented as polynomials, if you just plot the roots of unity on a complex plane, so here I plotted the four roots of unity, what we do with our Lagrange interpolated polynomials is we're saying that when you evaluate the polynomial at each of those special points, those 4 roots of unity, the resulting value of the polynomial will be equal to an element of your vector. Which means that if you then, well, if you just evaluate the same polynomial, instead of at some x value, if you evaluate at x times the 4th root of unity in this case, well, what you've done there is you just rotated all those points around by 1. And it's that rotation which enables us to get our right shift, because all we do is we take, if we go back to this slide, we take that z, a polynomial that represents those z grand product terms, and we evaluate it at x, and we evaluate it at x times the nth root of unity to represent both our output wires and our left wires. Feel free to talk to me after the talk if you want like more elucidation on how that works. But I'm not going to explain this, don't worry. This is basically the permutation argument put together. If you want to stitch together all the mathematics of how it all works out, this is what you need to check, this is what you need to compute. But the result of it all is basically you have 4 relatively simple equations that if the permutation check is satisfied, if your wire copy relationships are satisfied, they all equal 0 modulo the vanishing polynomial. And that's what gets us succinctness in our SNARK. Effectively, if you combine this with our arithmetic gate check equation, we have 5 equations that we can compress into a single verification equation by using random linear combinations. And the resulting zero-knowledge proof you get out of it, because again, you can then very easily turn completely mask the actual values of the polynomials you're committing to. So you can, all of the inputs to this SNARK second can be private, but you can still verify that you correctly computed, that you've executed the program that SNARK represents. What does this do, though? What does this get you? Well, I'm very excited about Plonk and about other techniques of this manner, because what it enables is genuinely transformative effects. Because you can now have private tokens on Ethereum where the transaction semantics, the logic surrounding your token, is governed by a SNARK. But this time, you don't need to run a trusted setup ceremony for each SNARK each asset that you're deploying. You can make private zero-knowledge dApps that can interact with these zero-knowledge tokens, where the transacting can be, the identities are hidden, the values that they're transacting are hidden. It's basically turbocharging what we've already built with Aztec 1.0 and just putting it on steroids, because it gives you enormous creativity and freedom in how you actually write your program, because you're not constrained by the limitations of either the EVM or of zero-knowledge proofs that become more expensive the more data you add into them. And finally, it also enables high-throughput scaling solutions, because you can use Plonk to describe, for example, like an Ignis or roll-up situation where you're validating 10,000 transfers at once. And the result is just a very succinct proof that is 576 bytes in size, and after EIP 1108 will cost 250,000 gas to verify. And all you need for this is a single trusted setup ceremony, and then to kind of bootstrap the crypto system, and then you can make arbitrary programs and circuits that all use the same setup. And this also brings me to, well, Ignition. It's our open source MPC ceremony. We need this trusted setup reference string, not just for Plonk, but for Aztec's confidential transactions suite of zero-knowledge proofs that we're launching in a couple of months. And so what we're doing is we're aiming to run one of the largest MPC ceremonies of this nature that has ever been done. The idea is every single participant in the ceremony has to generate a bit of toxic waste and add it to the common reference string we're producing. And then participants are supposed to destroy their toxic waste. Only one person has to act in good faith and actually destroy their toxic waste for the entire setup to be completely secure. And when you scale this to 1,000 people, when you have people from all over the place, from individual participants, institutions, major figures on Ethereum participating in the same ceremony, the chances of them all colluding, one has to assume vanishes to about 0. And so this is something that we are. This is the landing page for our ceremony. This thing is going to be going live in October, where we have a sign-up page I'll link to in a bit. But one of our senior engineers, Charlie, has put together a really quite impressive piece of kit where it's a very streamlined process. You log on to this system, you download some software, you run the trusted setup, you upload it to the server. This is all done relatively automatically. So we're hoping to scale this to hundreds of participants instead of just a few dozen. And if you would like to join us, if you'd like to sign up, that's a QR code that'll take you to our landing page, or you can just go to our website, aztecprotocol.com. The more the merrier, please. We're trying to get as wide a cross-section of the Ethereum community as possible to participate, because there's the implications of this trusted setup. We think, if we can put actually pull this technology out of a paper into the real world, will be quite transformative. Thank you very much.